Hey folks, I want to talk a little bit about the ideas from chapters 5 and 6 that we'll be using in this course and just get you on track with transitioning into the traditional methods that we use. And really what you're going to see is that we're just repeating what you did in weeks 3 and 4 from a interpretation and concept standpoint. But we're going to be using the traditional formulaic methods instead of the simulation methods that you've hopefully gotten comfortable using these past weeks. Cool. And at the end of this, there will be some examples, and so you'll see me click around in StatCrunch, at least for doing that. And if you need any R help, if you're doing R, reach out to me, and you can definitely do that, but all these things are in the software guides, as hopefully you've seen. And again, this will make the best sense if you've read through the chapter, or they're both chapters, the required readings a little bit. That will definitely help put these concepts in place. Cool. So we've used randomization tests and bootstrap intervals, and we can do both of these things for the most part. We can answer the exact same research questions of how large is something? What do we estimate it to be in the population? And is this idea true or not? A claim of some kind. We can answer all these statistical questions using formulas. And the main theorem that allows us to do that is called the central limit theorem. So we will pick that apart. So why do these two methods exist? Why don't we just have one and go with that? Well, I mentioned this in one of the face-to-face sessions, but basically, because computing power is required for doing these randomization and bootstrap methods, they didn't have that back when these ideas were being developed 100 and plus years ago. So they had to find a shortcut, and that shortcut are these theoretical things that you'll see, and these theorems, and the math, and the formulas. So the issue is that randomization and bootstrapping, they're much more intuitive. I mean, you can see physically a little bit more what's going on. They don't really need assumptions, not many, to work. So you can use them with what we would call bad data even. They still give you somewhat reliable results or valid results. Those terms can be a little dicey, but they're flexible. Traditional methods, they require more assumptions because you're not actually simulating anything. You're using theoretical formulas that require certain things to be true about the data or reality. Now, they're super fast though. They're formula based. You don't need to simulate anything. You don't need much computing power. You can do them by hand even, but you won't be doing that in this course. So like I came up through a little bit more traditional method, and I still enjoy them and I still use them because that still makes sense to me and they're very efficient. So point being, you can use either depending on the tools you have available to you. And that's a whole separate thing, but that's why both of these things exist. So we've got central limit theorem, and hopefully, again, you've read through the book a little bit so that this isn't the first time you're hearing this. I'm not going to build this thing from the ground up necessarily, because this video would then take like 2 hours with everything that's in here. So let me just try to get to the core of what's going on. What the central limit theorem lets us do is say something about the sampling distribution. Okay, remember that the sampling distribution is that thing that shows us the sampling variability. So it's like 1,000 different means from 1,000 different samples. That's the sampling distribution. The central limit theorem is about the sampling distribution. And what it says is that this sampling distribution, this distribution of sampling statistics, that when you've got random samples of a large enough sample size, that distribution, whether it's means or proportions, will be normally distributed, will follow a normal distribution, and will be centered at the value of the population mean or population proportion. We'll dig into that a little bit more, but just let that sink in for a moment. What it says, again, for a large enough sample size, that distribution of sample means or sample proportions is going to be normally distributed, which is the regular normal bell curve distribution that you've seen a lot of, and that it will be centered at what the true population value should be. Ideally, it should be centered at that. So that's pretty cool that that works. And that's what all inferential statistics that do not involve simulation are based on. And as we'll see with some pictures in a moment, that sample size changes some of our characteristics of our sampling distribution, our distribution showing sampling variability of repeated sampling from the population. So if we increase our sample size, some things happen. Well, the center of our sampling distribution stays the same. So we're still centered on the population parameter. But the shape of the sampling distribution looks more normal. It looks like it follows that nice, easy bell curve, which makes sense because when you have a higher sample size, you have more information about your population. So it's going to give us something that follows this normal distribution, which is a fact of just nature in the universe. Separate discussion. And also, hopefully this makes sense too, our error or our variability decreases. And yeah, there's a little formula there that illustrates that, but I think conceptually that should make sense to you, that the more cases you have, the higher your sample size, the more information you have, and therefore sort of the less variability in your means you're going to have, because you're going to have a much better estimate of the mean with higher sample sizes when you repeatedly sample from the population. So what does this look like a little bit? So there are three sets of things here. So what you're seeing at the top are three populations. So this is a population. This is all of the cases in the population that are normally distributed. And if you were to do repeated samples of size 2, that is, just take 2 randomly from the population, take the mean, and plot it, it would look something like this if you did it. This is probably 100 times, it looks like. Yeah. If you increase that sample size, then this tightens up. We're still centered at around 5, but now our variability of our sampling distribution is decreased. And we're looking a little bit more normal here. The really neat thing is the central limit theorem holds up even when our population is skewed or looks really funky, like this one, when it's multimodal. So as you can see here, if our actual population is very skewed, you can have a small sample size n equal 2. You can repeat those means, take samples repeatedly, get those means randomly, drop them on here. Yeah, it's a little skewed. It's fairly skewed. N equals 2 is not a large sample size. Well, what happens when you go to n equals 16? The skew is less severe. It's still centered around our population parameter of 6.81. And it looks fairly normal, and our variability is decreased. Same effect happens here. In this really crazy distribution, the population parameter, the mean, is 5. And when we do repeated sampling of sample sizes equal to 2, we get this funky shape, funky things going on. So we can increase the sample size and then say, yeah, that's looking a little bit more normally distributed, a little more bell-shaped, and still centered around our population mean. And the variability of these sample means is definitely decreased. So sample size is really powerful. But what's our threshold? we will get to that in a second. So there's a certain threshold of sample size, but that's some of the idea of what's going on here. Okay, so if that's central limit theorem, how does that help us make confidence intervals? How does that help us do hypothesis tests? Well, using the central limit theorem, if we have this normally distributed sampling distribution, what we can do is we can say that a confidence interval for the statistic in our sample is that statistic plus or minus some critical value. What we have been using is 2 from bootstrapping, if you remember that, times the standard error of the sample. So this is just a formula. This is a confidence interval formula using based on the central limit theorem. So the issue is, what is this z thing and where did this come from? Well, if we say that central limit theorem allows us to say that the sampling distribution is normally distributed, then we can use the normal distribution. The z-score is simply some distance over on the normal distribution. Again, the z-score is just some distance on the normal distribution. And so just like our bootstrapping distribution, we can get this idea of making a confidence interval by starting in the middle with our sample statistic, going out a couple of standard errors, and getting a confidence interval. Instead, what we're doing here, we're just using the normal distribution instead of the bootstrap distribution. We're still going out some number of standard errors like we did before, but now we're doing that dictated by this thing called z, instead of just saying 2. And we will see why we had picked 2 before. So what does this mean? So for example, if I want to make a 99% confidence interval, what does that mean for how many standard errors I go out? So in other words, what z number do I need to use to go out to make a 99% confidence interval? Well, in StatKey, you'll see that there's a place to bring up a normal distribution. Again, the central limit theorem says I can use this thing to answer my confidence interval and as you will see, to answer my hypothesis testing. In order to find the right z for 99% confidence, I just say, show me where on this distribution 99% of my values are captured on the normal distribution. Well, for the normal distribution with a mean of 0 and a standard deviation of 1, 99% of this distribution is captured by going plus or minus 2.575. That's just like the idea with the bootstrap distribution, where we go about up to and down to get 95% confidence. But now again, we're not simulating anything. We're starting with the distribution that the central limit theorem lets us use. So we're just saying, great, for 99% confidence, I know that that can be covered by going up 2.575 and down 2.575. So now you might ask, okay, what are some other z values that we can use? And this is where 2 comes from when we used that before for a bootstrap distribution. So that was sort of a trick. You were estimating the standard error using a bootstrap distribution, but I was still telling you to go up and down 2. So for our 95% confidence interval using a formula, we use a z of about 1.96. So we go up and down about 1.96 or about 2. All right, quick pause on to part 2.